everyone? Can one of you confirm you can hear me?
Good afternoon, sir.
Great. So we'll start the class. I was sharing my screen. Okay, so here we are. So in the last class, we were discussing the understanding of the learning theories as proposed by different behavioral scientists and psychologists, and how it has implications or what are the parallels in the machine learning. So in summary of that, we can say that human and machine learning can be compared through these graphics. Thus, in the human brain, the learning takes place through the 5 types of sensory inputs, which is audio, visual, smell, taste, and tactile senses. So these are the sensory inputs that go into the brain, and then the brain learns. In the end, the brain is capable of performing intelligent tasks, or you can say the brain has now become a trained brain or trained mind. In the machines, this model works in a similar way, but not exactly the same way. You expose your machines to different types of data. The data may originally be a signaling data, it may be an image data, category data, it may be static, dynamic, any kinds of data. And this data is then pre-processed, but before it is fed into the model, most often there will be a representation of the data in a new space, or there will be also, in addition, pre-processing of the data so that the data becomes suitable for the machine to understand. So you can say this data most frequently ends up into a numerical or logical data. And then this data goes into the equivalent of brain, which is a computational model, which is, in the case of machines, could be a linear regression model, multiple linear regression if there are multiple types of data or multiple variates, and naive Bayesian classifiers or any Bayesian classifier or regression models, decision tree, random forest, or support vector machines or support vector regression, artificial neural networks, CNN, or pretty much any, or you can define your own new model. So this model has to be selected. And this is before you start the training, you choose a model. And after you have selected the model, then you now expose this model to data. And then in the end, you will get a model through the learning, which is basically nothing more than a trained computer program. A computer program will be nothing, but it will take some inputs and it will produce some outputs. So this program can be considered to be an intelligent program because it has been trained on certain data in which the outcomes are predetermined. So in summary, machine learning steps, particularly the supervised, as I'll come to, it can be, so, yeah. Yes, Aditya.
So in the previous slide, isn't there a crucial difference between the two? That is that our computers are trained on discrete data, and that might not be the case with human brains. The data could be continuous.
No, I mean, in both cases, you can probably represent the data. So the transformations or pre-processing, in order to represent it suitable for the model, will always be there. So the computation model also may be different types. They may, some models can take only numerical data. Some model can also take categorical data. So there are different types of data. But in the case of brain, you are saying we can only learn discrete data. That is what you're saying?
No, I'm saying that in the case of brain, we also take input that is continuous, that is analogous. But in our models, it is very discrete.
Really not, because there is nothing continuous for the brain as well. If you break down to the level of neurons work only in a binary manner. They either fire or they don't fire. There is no analog output from the neurons. But it is just that the number of neurons involved is so many that they give a perception of continuity.
But how do they then process the data that comes from the external world, which has to be continuous? How do they pre-process?
So by continuous, you mean the time or the dynamic data, which is over time coming? That is what you're saying?
Yeah.
So yes, in the computer programs also, you have the dynamic data, you have the batch mode, and you have the programs, computer programs, which keep on learning with new data. So,
okay,
there
so
can
our brains also possess, our brains are also discrete machines in that sense.
At the ultimate level of the neuron, they are discrete. But neurons, because ultimately everything happens at the neuron level, and neuron works in a discrete manner. It's a very small unit, and the actual decisions are larger, which involve too many neurons. So because there are too many neurons and the number of discrete units is large, it may give you an impression of discreteness. For instance, when you take a visual input, so visual input is not continuous. There is a limited number of images that can be processed by the visual sensory inputs per second. Your eyes cannot receive, cannot interpret more than say 10 frames, I think, if I'm correct. So 10 frames per second. So if the data is moving faster than that, this will be overlapping. So for every sensory input, the amount of data that can be processed in a given amount of time is fixed. So that is because the image has to be processed and then it has to be converted and it has to be sent through the signal. So the same neuron will not fire again less than that time. So people have worked on in biophysics on how much information can be passed on to the visual input, to the auditory input, and other inputs per second. In terms of bits, they have calculated this. So this information can actually be computed, and people have worked on that, how much we can do. So does that answer your question?
Yes, sir.
Okay, so but good point raised. It gives us an impression that when we are seeing, for instance, if when we are watching a movie, it looks like that the movie we are watching the movie in analog, but it is not really. That is actually not really so. What we are seeing is actually frames per frame, and these frames are moving so fast that they give us the impression of motion. So it is just that, in fact, any analog system can be broken down into a discrete system if the discreteness is of a very high resolution. And well, this is digital versus analog, but brain also functions in the ultimate analysis, in the ultimate physiology. Brain also functions in a discrete manner, because neurons that pass on information from one part to the other part, they do not work in a continuous manner. They work either as they produce outputs in the binary manner. If the threshold is above a particular voltage, these neurons fire. If it is below the particular voltage, it will not fire. So they work in a binary manner. So they are also a kind of digital computers, our brains. And that is when you look at the artificial neural networks, that is where we draw the analogy also. We will come to them. So now we can break down the process of machine learning into 5 steps. I have made 5 steps. Somebody may add more or may want to put that some of this is outside machine learning, but typically when we are addressing a problem with the machine learning, we will start with data representation, data pre-processing, and after this, these are kind of pre-modeling steps. You also have to choose a model and hyperparameter of the model. Can you give me an example of how do we choose a model and hyperparameter of the model?
One example of a hyperparameter could be the earning rate that is set for the model. That is how vigorously we would change the weights of the model for any new given sets of error.
So yes, it draws attention to the fact that hyperparameters may correspond to the learning strategy and may also correspond to the architectural complexity of the model. So can you give me an example about the architectural hyperparameters?
Yeah, there's a parameter which seeks to make a model not very complex and not too easy.
Give me an example. Give me an example of a real model and what will be its hyperparameters. Other people should also participate and give me some inputs. Any real model. So for example, if you take artificial neural network, multi-layer perceptron, what will be the hyperparameters? Architecturally speaking, what are the parameters that user will set even before the training starts?
The number of layers of the neuron that.
Yeah, so you choose the number of layers, you choose the number of hidden units, and you also choose the connectivities, right? So these are the typical examples. In this case, you choose hyperparameters. And you also initialize. So initialization of the model, if it is being trained through a numerical process. There'll be no analytical solutions in this case, but some models have an analytical solution. So you do not have to choose the initialization. So yes, let me read the chat box. There is an answer here. So it says there are collaborative filtering models like alternative least square, etc., and dimensions of features. How many factorizations to perform are the hyperparameters? Yeah. So basically, the anything that you fix before you start the training, before you start exposing your model to the data, they will be sort of hyperparameters. And although in some cases you may have to change your model, if the model is not working, you may have to change the architecture of a multi-layer perceptron, but that is not actually considered to be part of the training, because that is like training multiple models and then choosing a good model. So anyway, the architecture, the structure of the model that you choose is done. And then after you have chosen this model, once you have started the training, you do not change the hyperparameters. This number of nodes are not changed, for example, unless you are doing something to optimize these parameters. So then the model training and training, it is the most crucial stage is the training. And you have to make sure that your model is not overlearning, or is not being trained too much, and it is actually learning. So the kind of balanced learning, which is a very important part, and also together with the cross-validation and together with the methods of regularization. So you have to find the best way to train the model with all the goals of the training that we want. And after you have done the training, you do not use any of the above, and you just do the deployment of the model. But in the deployment stage, the preprocessing stages and the representation stages that you associated with the model will continue, because the new data will also has to be processed in exactly the same way that the training data was processed. So now I'll take a quick look at what are the different pre-processing strategies before we apply machine learning. So you can think of the pre-processing steps in 4 groups. One is called data cleaning, and data integration, data reduction, and data transformation. So the purpose of data cleaning, I'll put down the points, but I'll take your inputs. You may have studied some of these points earlier. So let me take your inputs. What do you think is data cleaning? And why do we need it?
So the data might contain many null values, or the data might not be, suppose some model requires that all the data are numerical and some are categorical in that sense. And also we can perform normalization on it, because the values of one column may vary.
So normalization is not part of cleaning. So right.
Yeah, that would be at a later stage. Yeah.
So data cleaning basically means removing the data which is not useful for learning. You can say this. Or you can try to replace the data which is not correct. But most obviously, like cleaning is a process of removing the dirt, right? So cleaning is the data when you are removing those data items, or those data attributes, or those data tuples which are not useful for our learning process. So this may include like as you said, the missing value attributes.
Dropping irrelevant columns that we don't need.
Say again?
Dropping the features that we don't need and we think that are not useful.
Yeah, but that is feature selection. That's not really part of data cleaning. That is the attribute reduction or the feature selection. So cleaning basically refers to the removing of this data which is not consistent, which has some errors, or which has missing values. How do we deal with this? Is a very important point of the missing values, and that we have to address very often in our data. I'll come to them, but let me just quickly define these 4 categories. And the second is data integration. You can guess what is data integration. Can somebody tell me what is data integration in this context? So it is simply, let me summarize, because It's a subjective kind of terminology. So data integration is when you take data from multiple sources and put them together for learning. So when you integrate the data, there will be some challenges. Combining data from various sources, yes. So this is Karthik speaking. Input to the models. Yes, so if you take data from multiple sources, multiple databases, or data from the same lab or same group collected at different times intervals. So when you put them together, you need to do data integration. Data integration has its own challenges because the data that you are trying to integrate may have been developed on different schema. So then schema integration will be a big challenge. And data may have different quantifications in different sources. So data integration therefore becomes a challenging task in some cases. And then you do data reduction. Why do you do data reduction? You want to throw away some of the data, or you want to reduce the data by way of clustering or by way of selecting some data tuples.
Because you don't find these relevant to what you are trying to see.
So it may be due to duplication or redundancy. I'll come later, give a little more explanation in the next slides. So to simplify training and avoiding multi-collinearity issues. Yes, to some extent, but primarily we do the data reduction because of the duplication. So that is the most important reason that the data reduction techniques are applied. And attribute selection.
So why won't we count duplication in data cleaning?
Because data cleaning is the wrong data that you want to remove. So data is valid, but it is appearing twice, or data has overrepresentation of one group of data. So for example, suppose you are doing an opinion poll of a population. And in that opinion poll, there is a lot of data coming from one city. So any model that you now develop will be biased towards the group which is overrepresented in your data. So in the data cleaning stage, this data will pass because data is correct. So in the data reduction stage, you will remove the duplications or overrepresentations, right?
Got it.
Okay, then data transformation is where you involve the normalization and rescaling, because the data was collected at different scales, and also because the computational model itself may not be suitable to work on any scale of data. So rescaling and transformation. Sometimes we do transformation for reducing the dimensionality. And so transformation can be to create a new space in which data is transformed. For example, principal component analysis. Determination of principal components. So you, instead of working in the original space or original attribute space, you work in a new space. You find some transformation where all the information is retained. So that is data transformation. So now just quickly about these examples of data cleaning techniques. So one of the common challenges in the data cleaning stage comes that of the missing value problem. So you mentioned that if there is none in the data or missing value in the data, how do you address this? Without reading the slide, can you tell me, how do you solve the problem of missing values in your data? Suppose you are provided a data in a structured manner, a matrix where columns have the attributes and where rows have the tuples or objects, instances, and there are here and there are some missing values. How will you deal with this if you are applying a machine learning model? I'll collect your inputs and then I'll give you the summary that is written in the next slide. So some of them you can discover yourself. Yes, tell me.
One thing we can do, we can replace the missing data with the median of the rest of the data.
So here is Karthik again. Drop the row, take some statistical measure of the column over rows or various other values of the same row. So should I drop the row or should I drop the column if I have to drop it? So now one answer came from Aditya. So yeah, just let me collect your two answers. So Aditya said you can replace this value by some central tendency of the data. And then Karthik's answer is that you remove or drop the row. So if I generalize this, the point is that either we replace the missing values by some value or we remove the entire row. And I remove either the entire row or remove the entire column. what is more preferable? First, let us take the first point. That is, if I want to replace the missing values and by hand I want to fill it, what are the different options I can have?
The other thing would be to take the rest of the columns and make a model that could predict that column, and so
No, predicting is different. I'm not predicting now yet. So predicting will be another technique. So that will be third technique where we actually try to estimate the missing value. Yes, here we are not estimating the value. So there now we can, okay, let us say there are three situations or three methods to address this. In one case, we fill the value by just taking some central tendency. Second is try to, actually the first, I should say first is to drop the row or drop the column. And second, try to guess it. Guess it from the entire data by taking some kind of a mean, median, or any central tendency, or whatever tendency you call it. It may be a percentile. We'll look at different possibilities. And the third would be when we actually try to guess that I know these values, I know other attributes. So what would be the possible value here? That will be like guessing will be, this is called the imputation, or we try to predict the missing value here. This technique is called imputing the values. So let us look at the three first. So I think you have pretty much given me the three groups of techniques. We can go into a little more detail of this. So if I have to do the first one, dropping the data. So should I drop the row or should I drop the column? Columns have attributes and row have the objects. So should I drop the objects or should I drop the attributes? Depends on the context, but can you tell me what context? When will you drop row and when will you drop column?
We can drop the row if that row is the single instance of that column having a null value, then it would be wise to drop the row. But if that column has a huge number of null values, then we can drop the row.
Yes, one guide would be which of these has greater abundance of missing values. If the column has higher abundance of missing values, a particular column, then we can drop that column. And if the row has a higher abundance, we can drop the row. But sometimes these columns may be very important and we do want to have to understand their impact. So abundance may be one guide, but can there be another guide as well? Sometimes it may be logical to drop the objects, because if you remove the attribute, you are actually disturbing the schema or the inputs that are relevant for our predictions. But if you drop objects, then you are not disturbing the schema. So ideally, if you do not have any other guidance, dropping the object is better. But again, it all depends on context, as you rightly understand that the context here would be that where do we see a lot of missing values? If there is an attribute which has 90% missing values, maybe it is okay to drop it and it is not usable, unless the remaining 10% data is so important and so useful that I will be happy to drop the 90% data, but not happy to drop the 10%. So context, so guiding principles are the abundance of the missing values in an attribute or in an object, and also the relevance or importance, significance for our models. So this is one way. So what to remove. And second is to substitute this value by some central tendency. Now, what are the options? What central tendency should I use and how should I do it? Let us say this table here on the bottom, on the left, I have 126 columns or 126 attributes, and I have 2000 transactions data here. So transaction here refers to the data instance. So if there were some missing values and I want to replace them and fill the missing values, so tell me, how will you do? I give you three options and you tell me which one to use. So I can replace them by the, suppose I'm replacing them by average, or I'll then discuss when should I use mean, median, or other percentiles. So let us say I want to replace the missing values by the mean values. So should I take the mean of the entire table, available values, or should I take the mean of the column, or should I take the mean of the row?
mean of the column, I think would be
Why?
better. Because that is relevant to the attribute that is being discussed. Like if suppose there is an age attribute and we have some missing values, so
Yes.
I think the missing ages could be taken.
Yeah, because it depends on the data. If the attributes are all of the
Yeah,
same type,
that is.
there may be what types of attributes we have. If you have if all my columns represent some level of incomes of different say time points, so then we can perhaps average the entire table. But in some cases, like you give example of age, in one column you have age, in another column suppose you have the salary. So it makes no sense to average out the average age and salary. So in that case, the row averaging is totally wrong. But if different columns have different ages, age, everything has age, and attributes all correspond to age of one thing, age of another thing, etc. Maybe perhaps you can average it. So most logically and more frequently, each attribute is measured on a different scale, and each attribute represents an independent measurement. So it makes sense to average out only on the attributes on the column. So substituting the missing values by the column average will be more appropriate instead of the entire table. Sometimes we can replace them by the entire table average when we expect that all of my attributes are on the same scale and they carry the similar information. So for example, if I'm looking at the gene expression, one single gene, I'm collecting under different conditions and different individuals. Suppose in the row, I have the patient name. In the column, I have the conditions in which this gene is expressing. And all of them have similar value. In such cases, when all my columns and my rows are representing similar information, then I can take the entire table average. Then my average will be more robust, will represent the entire data in a more effective manner. But these situations are rare. More frequent situations will be when the attributes are on the different scales, and therefore taking the column average or attribute average will be most appropriate. Now, column and row is not the point here. The attribute is the point. This I have to specify because sometimes data is written in the reverse order. Attributes in the row and the objects in the column. So sometimes it is also done in databases because of the limitations on the size of array that can be associated to an object. So there's sometimes due to technical reasons, attributes are written in the rows. So fine. So you understand that if we want to take the average, we should take the average of the column. Yes, in columnar data stores. Yes. So now, if I have to take the average, now average is one of the central tendencies. Should I always take the average? Should I take the median? Or should I take some other central tendency or a static that represents the data that can guess the missing value better?
Depends on the statistical distribution.
Mean can bias if there are outliers. Yes, mean is, this is well known, that mean is a bad statistic to represent. Mean is usually not representative of the data. So therefore, mean, in most cases, when we do this kind of substitutions, we do not use mean. Median is better because it at least represents 50% of the data on one side, 50% on the other side. So in very special situations, we can use mean if our data is very well behaved, it is normally distributed, it has no skewness, etc. In those cases, mean will be a good measure. But in all practical cases, a median usually works better than the mean value. So this is how we substitute this. And then the third option was to predict what is called the imputation. So this is summarized here. You can ignore the tuple or the object. You can fill in the missing value manually. Use a global constant to fill the missing values. You may say, okay, wherever it is missing, I want to put it here. You can use a central tendency for the attribute, the mean or median that we just discussed. You can attribute mean or median for all samples belonging to the same class as the given object. And finally, when we do imputation, we try to guess the most probable value to fill in the missing value. And this can be done using a predictive model. So you can probably guess what this predictive model will work like. What will you do?
So can you repeat the question?
So what will you predict and how will you predict? Suppose I have a missing value here, and suppose my column T3A2 is missing. So how do I guess T3A2? What predictive model will you make?
We would drop the T3A2 is missing, right?
Yeah.
So I think in this case, we should drop the row T3.
No, I'm just drop option. This I'm just looking as an option. That is, I want to predict it. I want to impute. I want to guess what is the value here. So what will I do? Karthik said based on some of the other attributes, construct a model. So yes. So in this case, yes, Aditya, you complete? Yes.
Yeah, I'm saying that on the preliminary stage, we can calculate correlations with other attributes. And in that way, we can predict, or if we want to make a model, then we can set this attribute as the.
No, correlation will not give you the exact prediction. So for prediction, you need to develop a predictive model. And of course, your predictive model should not be very complex. Otherwise, even you are introducing.
No, by correlation, we can focus on those attributes which are strongly related to that attribute, right?
So you are again. So when you do a predictive model, you first do a feature selection. So you are trying to give a steps for the predictive modeling. So that may be valid. That is true for any machine learning model. But again, starting from where? Should I predict it from the rest of the A2 columns, A2 values, or rest of the T3 values? How should I guess the value of T3A2? Should I develop a predictive model to predict column A2 from the columns A1 to 126, A2 excluded?
Yes, that is what I would.
So these are two options that I have. I will try to predict the values of column A2, and in my input of the model, that all the values A1 to A2 126 will go where A2 will be masked. A2 will not be used. They will be used at the target values for the predictive model. So in each case, I can develop a predictive model. I will remove T3 row. Then I will write A2 as the target value and A1 to 126 minus A2 as the input values. And I can develop a simple linear regression model, multiple linear regression model, and that predictor can be used to predict the T3A2 values, right? So this is when I expect that this particular attribute can be predicted from the other attributes. But can I do the other way around also? Instead of doing it on the columns, I do it along the rows. That I try to predict T3A2 by removing column. Removing T3 and trying to predict the values of T3 from all the remaining column values. Is it also possible? So Karthik says, wouldn't that become the actual ML model we want to create? Not necessarily, because it depends on what is my target value. So actually all the 126 attributes of T3 we are trying to predict from the attributes of others. So this is not usually done, because in summary, we will try to see which relations are robust. Do we expect A2 to depend on other attributes? If each of these attributes is totally independent, there is no way to predict A2 from the remaining attributes. If there is some correlations, as you were saying, that you can test that there are some correlations, but correlations only capture linear relationships. So but in case there is some dependence of A2 on the other attributes, I can utilize the attribute modeling or attribute machine learning model. And for the T4, I can try to predict T3. I can try if I do the row on the basis of row, that means I'm characterizing how this particular individual is different from others. So I try to predict the attributes of T3 from the attributes of all other 1,999 cases. But this is usually not done, because in most machine learning models, you will have more data along the objects and less data along the attributes. And that is actually often the requirement for a good machine learning model in a classical context, to have more data along the attributes, more dimensions along the number of, fewer attributes than the number of objects. So the best is that we expect that these attributes are related to each other, and if they are related to each other, then try to predict this attribute, try to draw the actual machine learning model. So as far as the question that is it not producing the machine learning model itself? Yes, it is doing. In any case, you do it for the column or you do it for the row, you are both ways you are doing so. So it will be, for a large data, this kind of imputation may be difficult. So to do a predictive modeling, and then question will be, should I do a linear regression model for predicting, or should I do some other? So it depends on how important it is to impute those values. So depending, again, for instance, if you look at in the biological systems, if you collect the gene expression of single cell expression, there is one technology, you will find that in 70 to 80% of the data is a missing data. So how do we reconstruct those missing values? And it is very important to reconstruct. So this is solving the imputation problem, or solving the missing value problem, is still a very active problem of research. New methods people are developing. Sometimes you have to use all the attributes. Sometimes you have to select some of the attributes a priori. Sometimes you have to incorporate the domain knowledge into the system, so in order to guess the missing values more accurately. So all of these will go into this, but you broadly understand what we mean by imputation and what is the philosophy behind it. Secondly, another data cleaning technique is to remove the noise. So removing the noise means, what is noise? Have we discussed in this class before? What is noise in a data? When do I say my measurement is noisy? Yes, Karthik's answer. When there are outliers or randomness in data. They're two different things. Outliers and randomness are different. Outlier may be a very valid data. Outlier does not mean the data is incorrect. It may be that just one particular data object is behaving differently. It may be a very valid data. Sometimes it is the most useful data. Yes, Priyanshu, you're saying something.
Yeah, so the unwanted data or the meaningless information that has no correlation with the present data in the data set.
No, but if there is no correlation, it may be because of the valid reason. That's not noise. So a data which does not have the same behavior as rest of the data is not always a noise. It may be meaningful. Noise
might be the characteristic of the instrument that we are using to measure the data.
Yeah, so noise is basically incorrect measurement. That is,
incorrect.
You always measure something. What you have in your data is the measured value. There is no guarantee what you have measured is actually the case. So for any attributes, for example, you're writing age of the individuals. You go to a village and you ask everybody their age, and they report some age. So this age may not be real. Somebody may have deliberately given less age. Somebody may have deliberately given higher age, or somebody while writing may have made a mistake. So all these add to the noise, when basically you can define noise in general when the real recorded value is different from the actual value. And actual value nobody knows. All you know is the recorded value. So if, let us take this age attribute. I am collecting data about some population and I have the age attribute, and my age data is noisy. That means the recorded age is not accurate. So for instance, I was once analyzing the age distribution profiles of COVID patients. Now, anybody who goes to the hospital, the doctor will write their age, and now I want to do some analysis on the age dependence of the fatality, or any analysis I'm trying to do, or I want to develop a predictive model based on that. And if my data is now noisy, what do you think? How will you improve your data so that the machine learning models can be applied more effectively?
We have to filter out the noise.
Yeah, how will you don't know. I mean, people have given you their age, and now you want to deal with this age as an attribute for any model, machine learning or statistical analysis. You want to do something on this data. So how will you deal with this data, which you don't trust, or which you know has some problems? Quantize the data. What does it mean, quantizing the data? Quantization means, I think I understand what you're saying, and your answer is correct. But we can say it in a different language. So we do the binning of the data. Instead of using the exact age, I might use, yeah. So as you say we have age in years, we instead of create intervals of 5 to 10. So this is called binning. So data binning of the analog values can be one strategy. Yes, so this is one way of removing or dealing with the noise of the data. So now question is, how do we do binning in the data? So binning is not always same. You can do binning in 3 ways. The 3 methods are written on the slide: equal interval binning, equal frequency binning, and density-based binning. You all must be aware of them. Can one of you just explain what is the difference between the 3? And when should you choose one of them? So suppose I have a data vector. This age could be the example. I have the age values of 1000 individuals. Now I want to do a binning of this data. So how will I create? How many? First question will be, how many bins should I create? That is also, there's systematic methods to choose the number of bins in a data, but that later. But even the principle of binning, they can be done in 3 particular ways. Should I choose what comes to your natural thought is the equal interval binning. That means you will take the individual with the lowest age, individual with the highest age, maximum age in the group, and then you divide into 10 groups. And suppose the lowest is 5 and highest is 100. You want to have 10 bins. You will say 0 to 10, 10 to 20, 20 to 30, etc. So this kind of binning is very straightforward, and all of you have been doing it for a long time. So you draw histograms based on that. So this is called equal interval binning. That means each bin that you have in your data has the same interval size. Second is the equal frequency binning. So that is where we have to focus. So which is slightly different from equal interval. Can you guess what it is? And what is the advantage of equal frequency binning?
So equal frequency, I guess the number of values are same for all the bins that we have divided.
Yes. So if you have, suppose, 3 or 4 groups of people, so you will create the definitions of intervals so that each bin carries equal probability at the global scale. Because if each group has equal number of people, then you will not be able to see the differences. But you pool together the groups of data, and then you define the data in terms of quantile. So your quantiles could be 10 quantiles you are taking 100. So you divide in terms of percentile, or you divide in terms of decile, what do you call it? So 10 parts or 100 parts. And then so the principle is that in each interval, you have the same number of people overall. Now, if you want to compare the different groups, which group has a higher distribution in this bin than this group, then you will use those bins which have been generated at a global from the global data. And then individual groups can be distinguished from one another based on the populations in reference to those bins. So many times, I give you an example when this equal frequency binning or equal probability binning is very useful. So for example, in case of, again, gene expression, human genome will contain about, let us say, 20,000 genes, and you have 20,000 expression values for different conditions or different individuals or different cell types. Out of these 20,000 values, very often about 15,000, even more, of the genes will not expressed in any condition. So these 15,000 values are 0 values. And remaining 5,000 have some higher expression values, or sometimes just a few hundred, or sometimes just a few tens or dozens of genes have high expression values, and they are the real meaningful genes in that particular cell. Now, if you do an equal interval binning in this case, what kind of plot will you see in the histogram? All your data will go in one bin, right? Because so many of the genes are not expressing. So 90% of the data, let us say, is in the first bin. 10% of the data is in the remaining bins. Now, if you assign these bin values 0 and 1 to your machine learning model, you will get a big class imbalance in the data. And 90% of the data is in class 1 and 10% of the data in class 2. And if the bias, if the skewness of the data is even more, then you will get even worse kind of binning. And therefore, this kind of binning of the data, or this kind of discretization or quantization of the data, is not desirable, because it produces a highly imbalanced class data, which is not suitable for machine learning training. So many times machine learning will give you high accuracy and give you put all the data in the majority class. So that is not desirable. So in such situations, having an equal probability data is much useful. That although those values are close to 0, but you still are able to distinguish first 10%, then next 20%, next 30%, etc. So some kind of a ranking is involved there. But then there can be another situation when none of these two methods is working. Now, with this name written on the screen, on the slide, and with these two options that I already discussed, can you guess, can there be a situation when both these types of binnings will fail? So I explained to you when equal interval fails. Equal interval fails because there is too much of data in one bin if you divide the entire range into equal intervals. So you went to equal frequency, and equal frequency, what you did was you chose to have frequencies. Let us say you're making 10 bins, 10% data in each bin. Now this kind of binning will fail also in some cases, and that is where I'm asking you to speculate, where will it fail? Are you people thinking or waiting for my answer? Okay, let me answer. So this will fail if equal frequency intervals are such that data is not uniformly distributed throughout the bin. It is possible that you create, there is 1% of the data closely located, and then again there is an empty space, and then there is another 2% data there, and then again let us say 0.5% data here. If the data is not distributed uniformly throughout the bin, even in the equal probability, then the real information about the data distribution is not captured. And if you want to now create classes from the continuous data for the purpose of machine learning, you will feel that the data categories that you have put together, you say this is category A1 data, this is category 2 data. The classes that you are now forming are not really robust classes, because within that class there are clusters, some data on one corner and some other data on another corner. And in your binning, both of these two data are treated to be equivalent. So to overcome this particular situation, density-based binning has been proposed. Density-based binning says that you start scanning the data from the lowest value towards the higher value. So whenever there is more density, you choose one bin. Then go to the next bin. If the density is higher, you choose that bin there. And if there is no data there, don't choose that bin, and put the data to the nearest bin that exists there. So in other words, the breakpoints that you will define for such a data will be located on high density locations, which is not guaranteed in either equal interval binning or equal frequency binning. Do you understand this point? It is slightly imaginative, but I think you must have captured it. Just can you raise your hands, those who have understood this point of density based, why we need to do it and how do we do it? Karthik says yes. And any more? Are you people even there? Anyway, think about this. If those who have not bothered, I think I'll explain this once more, but in case, I'm not sure really it is so difficult, but since I'm saying it in an imaginative way without showing you the actual graphics of such a data, which could have been better, but the density-based, these density-based methods are also used for clustering, but here it is, we are using it for binning. So what we are doing it, suppose sort the data, and the sort in your sorted data on the, and put it on the scale on the, say you have numerical data from 0 to 1, and between 0 to 1 you plot graphs, and the at each location you see what, how many more points are there near to it. So if the data is now distributed very discretely in very different locations, and if you were to plot equal frequency graphs, or if you have to bin your data in equal frequencies, you might end up that there is a location where there is a high density of data. And if you, the same cluster of data which is located here, half of that will go into the bin on the left and half of that will go into the bin on the right. So this type of binning is creating wrong classes for machine learning, because the physical property of the data, or the numerical property of the data, is that this data together, which you have half split in one bin and half split in another bin, they have, in the final binning, this data looks too separated, whereas it should have been close. If you do equal density, you start scanning at each location what is the density of data points. When the density becomes shallow and when the density drops, you define a breakpoint. When the density is high, you avoid a breakpoint. That is how the equal density method will work. And in many machine learning methods, the right kind of binning, the right kind of class definition is very effective way of improving our model performances. Okay, so now the other ways of dealing with the noisy problem is that instead of define the clusters of the data point, that particular attributes, how the data is distributed there, and replace them by the central tendency. And then you can also use the predictive model just the way we were doing for the missing value. So here you treat each value to be a missing value and try to predict them and try to see how far they are from the predicted values. So the principle of missing values can also be applied to filling the noisy or replacing the noisy values by treating them each value as the missing value and trying to predict it in the way missing values are predicted, and then compare the predicted value with the observed value. If the difference is too much, either this will be an outlier or this will be a noisy observation. So now removing this noise every time is not desirable, because in most cases you do not know whether the variations that you're observing are due to some scientific reason, due to tangible reason, or this is just noise. So this is a big challenge, because many times we may mark some information as noise where it is very useful information. And you can also see discrepancies, which is similar to this predictive modeling. So,
sir,
yes.
Yeah, there must be some criterion. Like suppose if we do clustering, and suppose 90% of data clusters together very well, and some data is just scattered around randomly, then we can with some measure of confidence say that, right, that this
using a purely data-driven approach is not desirable in this case. You have to use the domain knowledge, because if you are studying a population, so suppose you are studying a population in Delhi, and you do observe that if you cluster the individuals based on age or based on some property, and you found that one particular group is very small, or there are just a few individuals. Now, both things are possible. Either these observations are correct, the recording of the data is incorrect, or there may be in Delhi, there may exist a small group of population, ethnic group or financial group, which is small in number or which is located separately. So this may represent a real information. If you just take it as a data-driven approach, you might discard it. So domain knowledge will often guide whether how should we interpret our clusters, or how should we interpret our densities. All right.
Yes, sir. Got it. Yes, sir.
Okay, so for today, I think I'll stop here. We have discussed some important points, and I'll take your questions from what we have discussed so far? You have been asking good questions, but I'll take your questions once more. So if there is anything remaining.
So as an extension, I would just like to ask that noise can only be deduced from the domain knowledge plus the various methods that we have seen. If both show us that there is something, then we can say that it's noise, but only one data-driven approach won't work. Because
it is some statistical principles give us some guide on when should we treat these variations as noise and when should we treat these variations as real. There's no real way to be very sure. So for example, as I gave frequent example of the gene expression, and gene expression distribution of values does not follow, it does not follow a normal distribution or Gaussian distribution. So very often what people try to do is fit a mixture model to it. Poisson distribution plus a random normal distribution. So most of the random noises are attributed to normal distributions because they are caused by random effects. So if you're making some measurements, the noise should not be all in one direction. If the information is getting biased only in one direction, it is most likely not a noise. So one important property of the noise is that it is random, and there should not be any systematic tilt in the noise quantification. So if your noise values can be, if you can somehow add the Gaussians, but what we know is that this noise should be random, should follow some kind of a Gaussian distribution. But what we do not know is what are the hyperparameters of that Gaussian distribution? What is the mean of that, and what is the variance of that? So if you can create multiple noise models of random, and you can write your distribution as a sum of Poisson distribution plus Gaussian 1 plus Gaussian 2, and these different Gaussians may represent, each of them may represent some kind of noise, which may be caused due to instrumental errors if you are using instruments to measure it, which may be caused by something else. So for example, if you are saying that there is a noise, let's take the example of age. Now, when people are reporting their age, when should I call their reporting as noise, and where should I consider the domain information here? See, if there is a tendency in this group to overestimate their age, then there will be a systematic bias. So this kind of a systematic bias is very easy to remove. If you know in some cases that this is how people are reporting their age 10% higher than what they are, or 10% less, or whatever. If you know that there's a systematic bias in reporting, this systematic bias can be corrected by simply rescaling your data. But that is not noise, that is bias. And that bias has to be detected. What is noise is that people are randomly saying their age is 50, they are randomly saying 45, somebody is saying 55. So if this is the random noise, so this is randomness, that cannot be corrected, and that can be estimated only by taking the kind of clustering the data and looking at the central behavior. So that is how you can deal with it. So in the case of machine learning, that is what has led to, instead of the exact models of neural networks, people have developed Bayesian models. So Bayesian models can address this kind of a noise because what you are predicting is within the probabilistic. So every value you have exact estimate that if the correct value is X, what is the probability that the estimated value will be X plus delta X? So you can compute the probabilities. So that way you can interpret noise in this context. So there you have to separate the real random noise from the biases, and both of them can be dealt with differently. And yes, domain knowledge plays a very important role. When you see different clusters, that is, domain knowledge plays a role in also interpreting outliers. Do we expect an outlier? And do we not expect an outlier, and this outlier is a noise or is a wrong measurement? So all these things will combine your knowledge of the data, your knowledge of machine learning models, together with the domain knowledge. In each case-by-case basis, you will interpret and find the correct solution to deal with the noise. Okay. All right then. Thank you for being here, and I'll